And for that, we need the position representation of the Schrodinger equation. All right, so position of a particle is an observable, right? And that's why it's an important part in, let's say, Heisenberg uncertainty principle. So there should be a position operator, which is a Hermitian as well as a self-adjoint operator. And the position operator, say, is acting on its eigenstate, which gives the position of the particle, can be labeled eigenstate by its position. Okay, so this is in one dimension. In higher dimension, the position operator would be a vector quantity, and it will be acting on a state, and its eigenvalue will be a triplet of vectors. Okay, and so what we can now do is that we can ask, for a general state psi of t, what does it look like in the position basis? So we take the inner product with x, and let's just say, instead of x, let's do 3 dimensions. So we call it, say, r. Then this inner product is a function of both t and r. And we call that the wave function. So what you saw in quantum 1 plus was essentially quantum mechanics formulated in this particular basis, okay? And that's how quantum mechanics was first discovered or invented by Schrodinger, okay? But its underlying mathematical structure in terms of a Hilbert space and operators acting on Hilbert space was proposed by Dirac, and then more rigorously formulated by Johnny von Neumann. Okay. So the Hamiltonian for most systems, if we exclude spin for the moment, will have the following form. The Hamiltonian operator will have a part which is the kinetic energy part, and it'll have a potential energy part. Okay. In the position representation, you can show that the momentum operator is given by minus I h bar, the gradient operator. So that in the position representation, P acting on psi of t, if you take the inner product of this with inner product with this with say r bra, then you get minus I h bar, the gradient operator acting on psi of r of t. Okay. So at some point, I might make you do an exercise to show this. This involves a little bit of, just a little bit of analysis. Okay, so we won't get into that right now, but it does. Well, delta functions and stuff like that. So the Dirac delta function and stuff like that. Okay, so in the position representation, P is given by this. Also in the position representation, X, the position operator, is just given by this X, the number X. And then the Schrodinger equation is given by IH d by dt, partial d by dt, acting on psi of RT is equal to minus h squared by 2m, because we have to take p squared here, see it here. And then we have the Laplacian operator acting on psi of r of t, and then plus we have the potential energy, which we're assuming to be time independent, multiplying our wave function. Okay, so this is the Schrodinger equation in the position representation. Okay, and in the tutorial, you were asked to derive these first two terms, and so let's make some observation about this first two terms. See that the first two terms has this form, right? So suppose that our particle was free, so v is 0, okay? Now let's let's take the complex conjugation of this. So the complex conjugation of this is this equation. So if I have a wave function psi that satisfies the Schrodinger equation, there must exist a wave function which is psi star, its complex conjugate, which satisfies this non-Schrodinger equation, right?
Sir, I was having a confusion regarding this. So
Yeah, exactly, I know. And
no, another one actually.
yeah, please.
Yeah, so like when we have a wave function, so we can decompose it into real and imaginary parts, right?
Yeah.
So then we plug that into the Schrodinger equation. So if that wave function is a solution, then are the real and imaginary parts solution as well?
No,
Okay.
no.
Uh,
The real and imaginary parts separately are not solutions, because the Schrodinger equation is a complex equation. So
right.
it
Okay.
mixes up
Yeah, yeah.
real and imaginary parts. Okay, so that is the whole point, is that the Schrodinger equation doesn't work without the I. So this equation, the second equation that I wrote, is also an equation that you could have derived, and that's what was the ambiguity at the end of the second problem of tutorial. And you should think about it, how this ambiguity can be eliminated. And I will post a note on that on Slack, but for now I want to concentrate on a different aspect. So the second equation is not a Schrodinger equation, it's the complex conjugate of Schrodinger equation. So, but if I take t to minus t in the second equation, what do I get? I get minus I h bar del by del t psi star plus h squared by 2m del squared psi star. So we see that the Schrodinger equation, gives us, something, some physical quantity, some physical state psi, and it evolves it forward in time, but it evolves the complex conjugate of this as well. But the price we have to pay is that we have to take t to minus t. This is the reason why the Schrodinger equation is able to, okay, one way of looking at this is the following, and this doesn't change if we include now the term v, right? The v term just goes along for the right. And what this means is that if I look at a microscopic system, say 3 particles interacting, and I take, say, some, somehow I take a movie out of it, and the movie is, the time is going in some way, and now if I turn the movie backwards, then these particles will go backward in time, And what this is saying is that the Schrodinger equation describes both the forward-going movie as well as the backward-going movie, where for the backward-going movie, the wave function is given by the complex conjugate. There is a more provocative way of saying it. The more provocative way of saying it is that Schrodinger equation is a time reversible equation. Okay. Now, those of you who have done some, I don't know, fluid and or stuff like that, you will recognize that the heat equation from thermodynamics has a similar, structure, or the diffusion equation, I should say. Well, I think the heat equation is. So it, this has similar structure, that it's a second order in time, first order in time and second order in space. But we know that the heat equation has a time ordering built into it, right? Because suppose that we have a distribution. Let's look at diffusion. Say we have a distribution of particles like this. Then as time progresses, it spreads out, right? Now, if I take it backward in time, then I get a delta function, a spike, which is unphysical. So, but the Schrodinger equation is valid going both forward and backward in time because it's a complex equation. Okay, so quantum mechanics is time reversible. At a microscopic level, the universe seems to be time reversible with some caveats, of course, which I won't go to. And the other thing that I cannot show you right now is that this complex conjugation means for particles which are charged that you also have to invert the charge of the particle. Okay, so if these were positive charges going forward in time, the Schrodinger equation would describe negative charges going backward in time, okay? Meaning that they would be both physically equivalent, okay? So, I mean, so this is a bit confusing. What I mean is that the Schrodinger equation says describing positive charges going this way. And then if you just reverse the film, then, what you would get is that negative charges also going forward in time, particles going forward in time, but in these directions, but now the charges have to be negative. Okay? So, I mean, this is kind of not the main focus of the course, because the main focus of the course is more nitty-gritty stuff, but I want you to be aware of this interesting, philosophical thing. Okay, any questions? I know you have questions, but, so that there might be questions that are outside the scope of this lecture, but, but let's have them anyway.
Sir, like we are talking about the free particle here, where V is 0.
Right.
But what if it does have some sort of V?
Yeah, if you add V, there's absolutely no change in the picture.
Oh, okay. So like if there is a diatomic molecule, that won't change.
Yeah, because the V term is also real, right? Like this term, it's also real.
Oh, I see.
I mean, the wave function is not real, but the operator is real.
I see. Okay.